next speaker. Anyway, thank you for sharing. Anyway, I think it's thanks for coming. At least we have a few magnets in the room. So that is good. Be good to discuss about how we can interact, right? So first of all, I would like to thank the organizer for inviting me to give the talk today. And today I'm very happy to talk about exchange-based and interface relationship phase in 2D Phan-Department magnetic heterostructure. Discuss about some important open question and perspective for the future research. So, how we enter the space 2D magnetism, especially like 2D Phan-Department magnetism. I feel very fortunate to meet two gentlemen who is a leading expert in 2D materials and magnetism. And we is very interested in this class of materials because it turns out that it shows a lot of exhaustive properties, and especially when you assemble with other materials, it turns out that new properties emerge as well. And another notice because 2D materials becomes very hot materials and attracts a lot of funding. That is kind of basically maintain the research in this magnetic community. Just come back to the history a little bit. Why is there's a new research trends in the 2D magnetism? So I hope that you can see clearly from here that the field of 2D magnetism began, which is on-cycle solution in 1944. Talking about the 2D Ising magnet. However, there's a lot of attention on this basically occurs when the first report on intrinsic 2D anti-ferromagnetic O-rings in 2016, and year after 2017, two important work on chromium iodide and chromium germanium tellurides. And they show that magnetic O-ring exhibits at finite temperature. So when basically the thickness is reduced to monolayer or bilayer. These two classes of materials are very interesting because it's an intrinsic semiconductor. However, it has very low TC, which is below 60 K. So for practical applications, it would be very challenging, especially for room temperature applications. Therefore, the continuous efforts has been made to discover the new materials that may have magnetic O-ring around room temperature. So 2017, 2018, we made the significant discovery of the strong room temperature ferromagnetism in beryllium-239 monolayer. And as the same year, almost a little bit later, basically the other group discovered the intrinsic metallic ferromagnet in the iron germanium telluride, the so-called FZT. So in this talk, I would focus more on this one because people use FZT as a materials and create a heterostructure based on this. However, both the VSC2 and also the FZTs are the metallic. So that's why it has a limitation to the optics, the response, which is only open to the semiconductor. And therefore, in 2020, we made another discovery where we show that it's possible to create a new class of 2D dilute magnetic semiconductor based on magnetically doped junction metal dichalcogenides. In this case, the valium doped tungsten disulfide and tungsten diselenide. And so in this talk, I could highlight a little bit the research which we performed over the year and also basically ongoing research. So the first work that I want to highlight here is the very strong room temperature ferromagnetism has been reported. And here we showed when we increase the beryllium selenide monolayer on basically Phan-Department substrates such as graphite and also MOF2. So in this case, we observe strong temperature-dependent magnetic properties, which is basically different from the film grow on the graphite. And later on, I show you that when we grow the film on MOF2, basically we have the strong interfacial coupling between the two layers, and also has basically charge transfer through the interface. That mediates the interfacial coupling between them. And that gives rise to the enhanced magnetism compared to just only the film grown on the graphite. After this discovery, basically 2D magnetism, especially the room temperature, become very hot. And even though the origin of the room temperature magnetism in this system still remain debate, because also the contribution from the defects, and it is very difficult to decouple the effects, contribution from the intrinsic magnetism. Moving on, so we basically wanted to create this magnetic O-ring at room temperature in the magnetic semiconductor. And I mentioned before that in this case that we wanted to, introduce the magnetic O-rings into the transition metal dichalcogenides. For example, in this case, it's the tungsten disulfide and tungsten dicyanide monolayer. So when we dope the small amounts of the vanadium, so we would be able to tune magnetization of the monolayer. And it's very interesting that we can create the 2D dilute magnetic semiconductor. And in this paper that we show that we can tune magnetization around 2% for vanadium doped tungsten disulfide and around 4% for tungsten dicyanide monolayer. This is the highest doping concentration achieved in this particular TMD, magnetic doped TMD system. And in addition to the basically tunable ferromagnetism that we observe, we also observe the very interesting, we call it thermally induced spin flipping, right? So why is this we call it thermally induced spin flipping? So in this case, when we dope the vanadium to the tungsten, so the vanadium will actually induce spin at the tungsten's at the lyrid and also the further distances. So it's very interesting, it's the magnetic moment of vanadium and also the moment at the tungsten at the lyrid distances, the anti-ferromagnetic coupling, which is different from vanadium doped tungsten disulfide, okay? Two different systems. So in this case, it's the anti-ferromagnetic coupling at the lyrid distance, but become ferromagnetic at further distance. So actually, we have weakly the anti-ferromagnetic coupling, and therefore, it's when you increase the temperature. So at high temperature, in this case, we see it's around 175 K. This temperature basically makes this coupling become weaker. And when you apply the magnetic field would be sufficient to flip, spin. And that's why we observe this crossover here in the magnetic hysteresis loop. And this turned out to be very interesting because it's 2D magnetic TMD system when it's assembled with basically other materials, especially for the magnetic electrodes for spin devices. So in this case, by controlling spin state, you would be able to control spin current or basically spin dependent properties of the devices. And going beyond basically tunable ferromagnetism through the chemical doping. So in this case, that we demonstrate for the first time that we would be able to tune 2D magnetism by laser light. And this thing is very interesting because it's given 2D magnetic semiconductor. Now, when you sight basically laser on the 2D materials, so basically you introduce the electron-hole pair, right? And so because the electrons being trapped at the defective side and also at the impurities band, so now you eventually kind of introduce holes into the system. So by increasing the hole concentration through the light, you actually basically enhance the magnetization. And therefore, in this work that we show that by increasing the laser intensity, we would be able to increase magnetization. So for further information, I would refer you to this one. And it turns out to be very interesting because eventually that you can control basically magnetism in the 2D limit, and it turned out to be optically, control magnetism and become very active research area. And I show you later that using this one, we introduce a new concept is called something like opto-spincaloritronics, because using the basically light, we can control the magnetism. Therefore, we can control spin current through the basically interface between ferromagnet and the metal. Why we need to explore magnetic interface phenomenon? It turned out to be very important because many of you gave talks the day before yesterday and yesterday, which we discussed about the basically, in most cases, the device structure, we not only deal with just only 2D materials. We assemble the 2D materials or make it into the heterojunction, which means that like, when you have the magnetic electrodes interface with basically 2D materials, you also really have basically something very interesting we call like magnetic porosity effect, right? And really depend on the nature of the materials, magnetic porosity effect become very significant. And actually in this case, we keep in mind that like, because it's 2D, and the 2D materials with the thickness just about like few nanometers. And when this is basically interface with magnet, so the magnet or magnetic substrate can magnetize basically 2D materials, introduce magnetic moment into 2D material, and it basically creates a new properties. So interfacial coupling between them, between two magnetic materials, this turned out to be very important. So I would not go through the whole detail here, but just give you one encapsulated picture of why the 2D interface is very interesting, because there's a lot of silicon advantages. And one of us magnetic interfaces turned out to be very important because it has a great interaction between the layer. So what it means that you can like Fourier the layer, and then you can basically stack layer of the different material together easily, which is very challenging for 3D conventional magnetic interface. So also in this case, it's like this flexible stacking is very important. However, for 2D materials, we have to be very careful because when something goes to just only few layer or like sub-nanometer, it's extremely sensitive to the air. So when it's open to the air, the properties can drastically change. That's something we have to be very careful. And then a lot of the groups basically, when they synthesize materials, immediately they report the properties. But when you transfer the material from one plate to the other plate, the properties don't really radically change. That's why when we work with magnetic TMD, we have to be very careful because eventually you may get not really intrinsic magnetic properties from sample. It could be oxidized sample already, right? When looking at interface effects, basically two important effects that we are considered here. This is exchange bias and also like magnetic porosity effect. So we know that exchange bias is a class of phenomena which is very important, actually has been explored in the magnetic recording head and magnetic memory devices. So in this particular case, we want to discuss about the origin of the exchange bias or like exchange bias mechanism, which is very important. So we know that like the exchange biases were reported in the cobalt oxide core shell nanoparticle in 1956, and then in the thin film system. So initially, the origin of the exchange bias were attributed to only like ferromagnetic, anti-ferromagnetic interface. But it turns out that like, and you can see from here in this review paper, I show that like exchange bias can be observed in many magnetic systems with different magnetic interface, including the ferromagnet, spin glass, anti-ferromagnetic spin glass, ferro, many different interface could induce basically exchange bias. Then the question we asked that like the ferromagnetic, anti-ferromagnetic is not only the condition to induce the exchange bias, and the interfacial, between them and the other hidden parameters that contribute to this effect. And here's some very interesting observation. For example, when mixed like bilayers, permalloy cobalt oxide, so ferromagnetic, anti-ferromagnetic, which groups observe something very interesting. So in the past, people only thought that, okay, when you create this like ferromagnetic, anti-ferromagnetic bilayer. So this coupling induces exchange bands. But it turns out that intermediate phase, that's in form of cobalt ferrite oxide nanoparticle, that it forms as the interface between these two layers. And that is contribute to the exchange bands. And they turn out to be very important. And this is basically, consistent with the recent perspectives that is basically discussed in detail in this review paper, where they discuss about like polycrystalline film composed ferromagnetic anti-ferromagnetic layer, and they see that like this sort of spin that it forms as interface between the layer, which contributes to the exchange bands. It's not just from the like ferromagnetic anti-ferromagnetic coupling. So the concept had to change. And this is basically, get along with the observation by Ali's group in UK when they observed the exchange bands in ferromagnetic spin glass. And more recently, in 2021, Nature Physics paper, they report about anti-ferromagnetic spin glass interface that induces exchange bands. So if you look at the whole picture like this, you think about the regardless the magnetic interface, if you have the basically this sort of spin that is formed as interface and it's coupled to one or the other, that could induce exchange bands. That's something that now to be very important. So our community need to look into this origin. So this is just like the simple picture. They show that when they highlight like all the anti-ferromagnetic and on the face and also the basically spin glass or like spin cluster that contribute to the exchange bands. So now going to the, something we believe this would be interesting and would be better because van der Waals magnetic heterostructures, the interface would be much better than conventional non-van der Waals magnetic materials. However, when we go through the literature and on the reports, people discuss about the exchange bands and like interfacial coupling between the layer. It turns out that it's not as simple as we believe here. So furthermore, in this case, we consider only like FCT. Okay, so FCT is, as I mentioned before, it's very interesting because it has a high DC, but its magnetic properties are extremely sensitive to the environment. So when exposed to the air, the magnetic properties change significantly. Especially for this guy, it's become oxidized at the surface layer. So you no longer have just a pure FZT anymore. And that's why when you form interface with the other material, you have to be careful because as the interface, you don't have the FZT, pure FZT. You may have the oxidized FZT as interface between the layer. And that changes the whole story. I would show you in the next slide that why we have to be very careful about this thing. So with all of the basically inconsistent report and observation, it's lead to the number of the important and open questions which I cannot discuss everything today, but just basically highlight some of the important questions that we may want to discuss, and hopefully that through this review that we will be able to identify some problem and try to solve the problem. Furthermore, in this case, that we wanted to see that whether we can't identify the intermediate magnetically disordered phase, the slight spin glass, is formed as the interface between ferromagnetic anti-ferromagnetic layer when we stack them together. And remember, it depends on how you make the materials. It's likely that this could be possible. And then when we form two magnetic materials together, we have now also the magnetic prosthetic effect. It turned out to be very significant in very thin materials. And now if you have two magnetic materials together, then you may have the basically magnetic prosthetic effect from both sides. And that is to contribute to the basically interfacial coupling. The question we asked, what is the role of the magnetic prosthetic of the ferromagnetic layer on the exchange bands effect in this particular system, right? And when we form the interface between different materials, it's also the possibility that you have the charge transfer across the interface. So how the charge transfer become possible and how the charge transfer mediate interfacial coupling between the layer. That's something that we have to look into as well, because there's many studies that they show, for example, the chromium iodide, when they form interface with tungsten disulfide monolayer. The opposite is basically the charge transfer to that one, and it changes the base interfacial properties drastically. Similar, the FZT form interface with basically WS2 monolayer. It also shows that the magnetic anisotropy drastically increase because of that possibility. And to that important question we ask, can we achieve the exchange bass at room temperature, which is very challenging, right? Especially for this particular system. So this means that we need to look for the ferromagnetic materials that has the TC is way than room temperature, and we need to basically assemble it with materials that have the near temperatures also at a very high temperature as well. And then the last question we ask is because can we manipulate, can we control the exchange bass or like exchange magnetic anisotropy or interfacial anisotropy using the external stimuli, for example, like electrical field strain or actually light, which we will discuss in our study as well. So in order to address all of the important questions, we may have to go through all the basically the different cases where you have the different types of interface. I would not go through all of the cases I discussed in this review paper, so you can refer to this one. But this turned out to be very important, and we listen to so many interesting talk where they discuss about the basically magnetic electrodes, even graphene or 2D, junction metal dichalcogenides, the magnetic positive phase play the important role, and that would change interfacial, like the magnetic properties and spin, transport as well. And here we just give you some important example, which we have to be very careful when we characterize, magnetic properties. For example, in this case, we discussed about FZT. So FZT turned out to be very interesting because basically it shows very high TC in the bulk form ferromagnetic. So depend on the materials, but TC would be around 200 and 230 K. Interestingly, when you reduce the number of layer, and this is basically below 10, so you see that it decreases the TC drastically, right? So if you want to use it for, monolayer for the devices, then of course, TC is very low, right? This means that it's similar to chromium iodide or other types of materials, the TC is very low. However, in this particular case, when they electricals by getting it, so you see that TC is increased up to room temperature. So eventually that you can manipulate the TC of the monolayer or field layer up to room temperature, make it interesting for application, right? So that's also the reason why FZT turned out to be a very interesting candidate for various spintronic device applications. When we look into the interfacial coupling between the layer, because remember in this case we have only the FZT, but when FZT is exposed to the air, it doesn't matter that whether you control it in some way, but when you do the measurement or expose it, with a few minutes, the surface layer becomes oxidized. If you see from here, even it's protected by aluminum oxide here, but you still have the oxidized FZT layer right here. And people believe that because of the coupling between two different layers here, that leads to the exchange coupling or exchange bass. And they observe that below 120 K, exchange bass is basically increased with the lowering temperature that you can see from here. However, the exact nature of the magnetic O-rings within the basically oxidized FZT layer is still unknown. And the idea is just due to the interfacial coupling between ferromagnetic and anti-ferromagnetic layer that induce the exchange bass may not be possible. So if we look at the interface between them, so we see that we don't have a really flat interface between them because it becomes oxidized. So it's very likely that you may have the kind of spin disorder right here. This is more like a spin cluster, and then you have the kind of ferromagnetic here. So it comes back to the story where you have the ferromagnetic spin cluster or spin cluster layer, and that coupling could possibly induces, like the exchange bass, right? So now, if we interface the FCT with other materials, so we have to be very careful because many reports, they try to basically form the interface between FCT with like anti-ferromagnetic van der Waals materials, for example, in this case. So when they form the interface with the anti-ferromagnetic van der Waals materials, and they show that, okay, the coefficient increase compared to the FCT, and they observe the exchange bass. If you look at this one, so you see that, okay, exchange bass, appears below 120K. And remember, as I mentioned in previous slide, below 120K, where you start observing the exchange bass in FCT, which is become oxidized at the surface layer, right? So in this case, they show that, okay, FCT by itself did not show the exchange bass, and that's why they conclude that the exchange bass will come from the interface between FCT and anti-ferromagnetic layer. But keep in mind that, like, if you have the surface layer, which is very thin, on top of the basically FCT, the coupling may not be sufficient to induce the exchange bass, but now if you have the anti-ferromagnetic layer on top of it, you may be able to see the exchange bass, right? And the most recent report that they look into the, like interface very carefully. If you look at this one, cross-sectional high resolution TM imaging, they show that clearly between FCT and anti-ferromagnetic layer, there exists an intermediate layer which is related to the oxidized FCT. And when they expose to the air, clearly what they observe is the exchange bass is about like 3 or 4 times larger compared to just flat layer. So this is kind of like consistent with what I suggested. and in this case, the coefficient basically decreased compared to the fresh sample. This can be understood because basically when you reduce like the pure FCT magnetic volume fraction, so eventually the TC is decreased. And the increase, like oxidized FCT layer. So this means that like previous study or many other study when they claim that the interfacial coupling between ferromagnetic, anti-ferromagnetic, which induce the exchange bass and it changes the properties may not be, precise. So we have to be very careful. And this is like another 2 example which we still like argue about. So for example, in this case, in terms of forming interface with van der Waals anti-ferromagnetic material. So in this case, they formed like interface with iridium manganese, which is anti-ferromagnetic, and near temperature is about like 700, about 700. So the near temperature materials in the bulk form is way higher than, the TC of FCT, right? But they do show that, okay, they observe the exchange bass here. On the other hand, you have the interface between ferromagnetic and also anti-ferromagnetic CZT and nickel oxide. If you remember, like this one actually given by Ichiki from Japan yesterday. So he thought that, okay, it's only due to like strain, because he believes that like strain induced by nickel oxide when it forms the interface. That would lead to the enhanced coefficient field and also the magnetic anisotropy. However, what we consider here is because like nickel oxide has the real temperatures way higher than room temperature. So eventually, when you form the interface with this one, and this one have DC just like 60K, so way is lower. So that wise, like when they perform magnetic measurement, magnetic hysteresis loop in the temperature regime, where they look into it, they would not be able to see the shift. Then people can argue that why they observe basically exchange bass in this particular case. And remember, in this case, that you may have the like oxidized FCT layer in between. And that's induced basically exchange bass. And keep in mind that the CZT is not like the FCT is quite robust regarding to the basically oxygen. So because of that, we have to basically be careful. For example, in this case, that we believe that this could be due to the ferromagnetic, anti-ferromagnetic coupling, but eventually oxidized FCT layer may play an important role here. Now we consider the different cases where we have like ferromagnetic or like magnetic insulator, yttrium iron garnet, and you know that like when we form the like TMD materials with magnetic materials, so we would expect that magnetic materials induce magnetic moment on basically like TMD monolayer, and in this case they show that clearly when they have this like MOS2 monolayer on top of yttrium iron garnet. So they show that like magnetic moment is induced on the monolayer, but they argue that like interfacial coupling between MOS2 spin and also yttrium iron garnet spin is an anti-ferromagnetic coupling. But there's no clear evidence for that one. And of course, we have to consider something that is very important because the TMD always have the kind of defect. And in this case, they even consider the defect, you know, like play important role as well. So in our recent studies, so we look into a very interesting system. So the first thing would be basically like the magnetic substrate we consider here is the iron. The second one is basically tungsten diselenized monolayer. And we consider the different cases. This is just piston. And the one with the piston with the defect, and then we is basically dope. When we dope, and then we dope and also have the defect, and when we had just had only the defects. So we see that this is really changed, you know, like how magnetic substrates induce magnetic moment on the monolayer. In this particular case, that we see that also basically poised in like in ferromagnetic. But when you dope vanadium, so we see that like vanadium magnetic moment and the nearest spin at the tungsten side, which is anti-ferromagnetic coupling, which is kind of consistent with what we observed before for vanadium doped tungsten diselenized monolayer. Very interestingly, when we, you know, like look at the basically spin Seebeck coefficient, and it turns out that when we form the interface between iron and platinum, that we see that basically these coefficients increase, and this means that like you can enhance spin to charge the conversion efficiency by forming, you know, like TMD semiconductor 2D materials in between, and this result explains very well the experimental observation of the giant spin Seebeck effect in yttrium monolayer tungsten diselenized platinum heterostructure observed by Professor Kim groups in Korea. So now just go to basically the final, you know, parts which we discussed about, very interesting, but we consider like defective magnetic van der Waals interface. Just to bring you back to basically the system that we you know highlighted before. Vanadium selenium monolayers grow on the graphite and also on the MOS2. So in this case, clearly we see that like when you grow on graphite, you see the magnetic histograms look very clear from both you know VSM and also from MOX. However, like temperature dependence is very weak compared to basically the vanadium and VSC2 monolayer go on to the MOS2. So in this case, as I mentioned before, that's like interfacial coupling between the two layers, because MOS2 is known to have the defect induced magnetic O-ring. So you have the spin that is induced by the defect from the MOS2 coupled with the spin from VSC2. And also, when you form the interface, you have the charge transfer, which basically, you know, like promotes or enhance the magnetic properties from both sides. So that basically makes them couple very well. That gives rise to the enhanced magnetism in this particular case. Because of this thing, so VSC2, MOS2 turn out to be very interesting system to explore like magnetic positive effect and also the exchange bass. And here's basically what we look at, right? So when we grow on graphites or graphenes, we see that, okay, magnetic his loop much smaller, so we consider more like defect, or sorry, subtract-free, like magnetic properties. But when we grow on the MOF2, now we see the enhanced CrSe field and also basically the exchange bias is observed in this case as well. So it's very significant exchange bias when we cooling down the system in present magnetic field, right? And if you look at this one, it's very interesting. It's not only shift, but also the basically increased CrSe field and change the shape as well. So what's happening? So, as I mentioned before, because basically when we look at like interfacial coupling between VSE2 and MOF2 spin, so when you apply strong magnetic field, especially in this case 1 Tesla, it's sufficient to align, basically meets a line spin from the MOF2, and therefore it's enhanced magnetization and also makes the loop more like rectangular. So that's something that we observe in this system. And the feature is very different from the film grow on graphite, because in this case we don't see any exchange bias, right? So it's clearly confirmed that it's come from the interface between MOF2 and VSE2. When we perform the magnetic hysteresis loop measurement at different temperature, and here we plot the exchange bias field at function temperature, and we see that it's increasing and drastically increase at lower temperature. We also investigate effect of the cooling field on the exchange bias, and we see that exchange bias field increase and then decrease. And this is basically can be understood, considered like more like have a spin configuration from MOF2 interface with the VSE2. So it means that when you apply magnetic field, the magnetic field would basically align spin in one particular direction when you're cooling down the system in present magnetic field. But when the magnetic field is very large, so it's actually larger than the critical field here, is kind of separated and just align them with the field direction. That's why the exchange bias now is basically fields a decrease, and it could potentially disappear at a very high magnetic field. So in this particular system, we want to see that if we can tune magnetic properties of VSE2 side, can we change the exchange fields of the heterostructure? And in this case, that we change the ratio between vanadium cyanide, and we see that exchange bias also change as well. We also change the morphology, and that's also to basically change magnetic properties of VSE2 monolayer. And that's also change basically the exchange fields of the heterostructure. So it turns out that effective interface between the TMD materials by themselves can also induce exchange bias, and we can potentially enhance the effects. So this comes to basically some summary, and here we show you that very interesting strong tunable room temperature magnetism can be achieved in metallic VSE2 monolayer, and also in the new class of 2D dilute magnetic semiconductor based on magnetically doped TMD monolayer. We show that we can control, we can manipulate the magnetic properties using optic mean, and that's something that we discussed here about two important effects. It's the exchange bias and also magnetic positive effect. And in order to understand the origin of this one, we have to take into account many different factors. So I did not mention, but something that we have to keep in mind as well, that when we form the interface, that you also have the charge transfer, you have also cell intercalation as well. So all of those can contribute to the interfacial coupling. And the last point that I want to point out that further research is need to be done to see that how we can control the exchange bias effect or exchange magnetic anisotropy using the external stimuli such as electrical field. So far I got one publication where they show that they can control the interfacial magnetic anisotropy using electrical field, which is quite interesting. So just choose basically the kind of like a very new and interesting research direction which we propose. So in this particular case, just go back to like spin coverage devices where they, there is a spin current from the magnetic material through like interface between ferromagnetic material and metal, which in this case platinum with a strong orbit coupling. So the idea is like when you create a temperature gradient and it has the blind multipliers, you create a spin current, and the spin current is converted into spin, like charge current through the inverse spin Hall effect. So you eventually can probe the change in the voltage here on the platinum. Interestingly, which we have to consider, because basically in this case, yttrium's iron garnet is magnetic insulator. And when it forms interface with the platinum, it's a metal. So metal insulators basically have very large conductivity mismatch, which is basically, kind of limits like spin charge conversion efficiency. So in order to enhance spin charge conversion efficiency, we introduce very thin layer C60, because the C60 is basically based on the carbon, and the carbon, just like the graphenes, it basically has like weakly spin orbit coupling and has a long spin diffusion length. So what it means is like when you have basically organic semiconducting layer C60 here, this one eventually reduce conductivity mismatch between yttrium iron garnet and platinum significantly. So our DFT calculation shows that like by introducing the CT in between, we can radically increase the density of state right here compared to just only, like yttrium iron garnet and platinum. And with that, so we can enhance basically spin-Seebeck effect radically. So this is basically show that it's possible to enhance spin-Seebeck or spin charge conversion by introducing very thin layer of semiconducting materials. And C60 is a very interesting material because when you form the interface, it tends to basically change the surface of the material as well. So in this case, what we detect is that like C60 reduces the surface magnetic anisotropy of like yttrium iron garnet, and that basically enhance the effect as well. So eventually, C60 not only reduce conductivity mismatch, it's also enhanced spin mixing conductance, and that is enhanced basically overall spin charge conversion. So with this one, we limit to just only 5 nanometer thickness. When we try to go down to like 1 or just like 1 nanometer thickness, that is very challenging. We would not be able to achieve using the existing thickness. So we think about like magnetic TMD monolayer. Number one, magnetic TMD's monolayer is a semiconducting material. So it's similar to C60. When it's inserted between the yttrium iron garnet and also the platinum, it's also reduces the conductivity mismatch between them. Number two, it has the magnetic properties. So eventually, you enhance basically magnetic density as the interface between them. That's why you can radically increase spin mixing conductance. Therefore, we would expect that like this would enhance spin Seebeck effect significantly. The group from Korea, they use only the like TMD monolayers. It's not magnetic TMD, and they show that it's an enhanced effect. So in this case, what we propose that like if we use a magnetic TMD monolayer, we not only enhance the spin Seebeck effect, we can also control the magnetic properties, using the laser light. So this means that like we can basically control the spin charge conversions using the optic mean. And that's basically lead us to propose a new research field we call like opto-spincaloritronics. And this is remain unexplored. So hopefully that like future research would focus more on this one. So with that, I would like to thank like of my group member, like former and current PhD students and postdoc, and of course my collaborator who's basically made a significant contribution to this work. And thank you so much for the attention.
Thank you. Thanks for your talk. Anyone to ask questions or comments? Yes.
So thank you for the very nice talk. I have a very basic question just about terminology. I mean, what we call proximity effect is, say, the effect of the magnetic layer on, say, a non-magnetic layer, right? So it introduces some kind of magnetism. And what you call exchange bias is, say, the reverse effect of the non-magnetic layer that is shifting, say, the hysteresis loop of the magnetic one. Is that true?
So in this case, like we had to distinguish between two effects. So exchange bias here is more like related to the magnetic interface. It's not between the magnetics and also the non-magnetic interface. But the point that like it's kind of in between. Mm-hmm. So for example, like TMD, like pure TMD would not has magnetic properties, but because of defect, that's why it has like spin, polarized spin as the defect side, and eventually now it becomes kind of defective magnetic materials, and therefore, for example, in this case, when I show you VSC2 and MOF2, it's also induced exchange bias, but plus it's basically like magnetic positive effect. That's why when you cooling down the materials in present magnetic field is not only basically shifted, but also basically aligns some spin which is misaligned from the MOF2, and that turned out to be very interesting. So we also look at basically completely different system, not VSC2. It's just like TSC2, which is like non-magnetic. So when TSC2 has a defect, that is also kind of defects interface, and we also observe the exchange bias. So it turned out to be very interesting. It's kind of combination. So that's why this system is kind of interesting to explore both the exchange bias and also like magnetic positivity effect. Yeah.
Thank you.
Thank you.
Any more questions? No. Thank you again.
Thank you very much. Thank you.
Thank you for your